Hello, hello. Good afternoon, Daniel. Good afternoon. Awesome, awesome. Can you, good afternoon. Could someone, I'm not sure about my audio. Could someone make, well, first of all, can you hear me? And second of all, could someone make a sound so I can see if I can hear you?
We
I
can hear
can
you.
hear you.
I'm going to say good afternoon. You cannot hear me, can you? One sec.
Yes, we can.
Oh, you can hear me. Oh, right. Okay. I could not. You can hear me. Okay. Try again. Now. See if I can hear
Hello,
you.
can you hear us?
Ah, yes. Okay, great. Thank you so much. All right, great, great, great. Thank you. Awesome. Okay, so I will start again. So good afternoon, Daniel. Good afternoon, Sam. Hello, Ashley. I'm good, thank you. And I love that picture. That picture is so free. Like I so think that's real. Anyway, okay. Good afternoon, Nikaya. Good afternoon, Alyssa. Good afternoon, Mariam. Uh, Good afternoon, Jenna. Good afternoon, Jerry. Hello, Jennifer. Good afternoon, Darina. Thank you, Ashley. Thank you, Sam. Hello, Stephanie. Okay, and I'm still assuming that you can still hear me and I can still hear you. Okay, okay, awesome, awesome. So we're gonna get straight. Wait, did I say everybody? Darina, Jennifer, Jenna, Stephanie, Sam. And you notice we do have school today. I know there's a lot of confusion about that over the weekend. You all figured it out. That was crazy. But yes, today is normal. Well, sort of. Okay, I think this Alyssa, hello. Jerry, hello. I think I said hello to everybody. Okay, okay. So let's get, we are going to, oh, sorry. Okay. We're just gonna keep going. Again, I'm a little bit behind you guys. Well, I'm still behind you guys. That's good. As long as you're a little bit ahead of me, we're both good. There probably will be new homework posted soon, but not until I catch up with you. So as long as, soon we're gonna get to homework 2 finally, but we're away from homework 3, so don't worry about anything until you do. Okay, anyway, I'm just gonna keep, we're making progress. We're almost done with one. I'm just gonna keep going. Stop me if there's any questions or if you can't hear or anything. But luckily, I think we have 2 questions left on homework 1. The last one will take a while. The last one is the big point of everything. But let's do the second to last one first. And again, stop me if I'm in the wrong place, but I believe we finally got through questions 1 through 5. 1 through 7. I think we have question 8 and question 9 left. Again, stop me if I'm wrong, but I think we have question 8 and question 9 of homework 1 left to do. So here we are. just to, I'm repeating the question as usual. If the diagram, that's one, right? Diagram, fact pattern. I repeated the question, that's two, WIQ, whatever. Now, I just want to make clear, well, I think it's clear, but we're going to ask, does each of the following quantities go up or does it go down? Or does it stay the same in terms of magnitude, right? So we're going to ask three quantities: velocity, acceleration, and jerk. We're just looking at the magnitude of each. So it's the magnitude of velocity, which is called speed, right? We're only asking the question in its first sort of segment of motion. We're only asking this question in the first quarter of a cycle, so to speak, right? Just from x equals 15 centimeters on its way to x equals 0. Like other things will happen after that. We're just not asking about that at the moment, right? So first we're asking about the speed. So I'm going to go on to the next page. And for these questions, I think a lot of you got them, at least the first two, very right. So I'm very happy. I'm moving a little slow. Like if anybody wants to say anything, like contribute an answer or a thought or possibility, please do. Because I think a lot of you are clear on this one, but like, okay. Well, okay. I guess I'll cut to the chase. I'm going to say, and I think a lot of you got this right. It's not supposed to be a trick or anything. I guess I'll just say, I think it increases, right? And I'm going to say that. Right? I don't need anything more complicated than this. I mean, the object starts at rest. By the time it gets to equilibrium, it's not at rest. It's moving at a high speed, a speed that we figured out in part 4, a speed of 3.87 meters. There's not much more to say. I mean, it's not meant to be more complicated than that. So the object is getting faster and faster as it moves. Okay, stop me if there's an issue, but that's all I'm looking for there. Then now notice it gets a little bit more complicated here. Just to pause for a second. Notice the magnitude of velocity is called speed. Like we have a word for that. But there aren't two different words for acceleration, which is one of the reasons that people start. I mean, things are hard enough, but it starts getting a little confusing that the magnitude of acceleration is called acceleration. Like just remember that you don't have English like triggering your brain as helpfully as you do with the first derivative. In fact, let me in fact make clear like what we were just asked about. I mean, I think you know this, but we were first asked about the magnitude of the first derivative of the first derivative of position with respect to time. Now we're being asked about the second derivative, right? Right. So what happens to the magnitude of the acceleration? Let me, in fact, before I even answer that, let me add another layer of potential confusion, or one of the reasons we have to be so strict about magnitudes here. Like, whatever the acceleration values are from 0.15 meters to 0, well, first of all, they do vary, right? I mean, I think most of you got this right. In fact, I think all of you that turned this in got this right. But like, let's make no mistake, right? We're not in constant acceleration land anymore. That's why we had to do all this energy analysis in questions 4 and 5. So the acceleration certainly does vary. But all the acceleration values that we're getting from the beginning to the equilibrium position, they're all negative values, right? They're all negative, just meaning that they're pointing to the left rather to the right. That is true, and I don't want to say that it's not. but that's one of the, so it can start getting confusing, like if negative numbers are getting lower or higher, like what do we call that? But again, remember here, they are all negative, but all we're asking about here is the magnitude, right? So the magnitude of the acceleration, if you just look back at your answers from question 2 and question 3, the magnitude of the acceleration at the beginning is 100 meters per second squared. Yeah. And the magnitude of acceleration by the time the mass gets to the equilibrium position is 0, because in fact, that's the definition of equilibrium, where the acceleration is 0, right? So I think the magnitude of accelerations are decreasing. Put another way, the force is getting weaker and weaker as the mass is pulled in, right? The force is proportional to displacement from equilibrium. So the force is getting weaker and weaker. So the magnitude of acceleration is getting lower and lower. It's going from 100 meters per second squared to 0. So, and I think most people got this right. So, okay, wait, I'm going to totally look at that in 1 second, Sam. Let me just write this before I forget, but let me look at that. Let me just see what Sam's in the chat here. Great question. Yes.
Because I was getting confused when I was doing this homework part, because acceleration's decreasing and the speed is increasing. So would they have to be in the same direction for the velocity not to be slowing down? I don't know if that makes sense.
Oh, no, it totally makes sense. In fact, that's why I just paused and was thinking, no, that makes a lot of sense. On the one hand, you're tapping into something that I totally want to talk about. I mean, partly you're tapping into the whole purpose of this question, and I want to say something about that to everybody. But also, you are saying something I want to think about for 1 second. No, you're definitely, it totally makes sense. Okay, great question. No, sorry. Okay, for a second, that almost actually threw me. No, that is a great question. It is part of the purpose of this question. There's a lot going on with this question and with Sam's question. Okay, on the one, so I'm going to write an answer to what you just said on the next piece of paper, on the next sheet. The first thing I just want to point out is, I mean, one thing that's not confusing her. I know what she's asking, and there is a depth to this. But one thing, before we get to the details of what she's asking, what Sam's asking, yes, do notice that what's happening to the speed is one thing. What's happening to the acceleration is another. Like they're not doing the same thing. And that, right, one's going up, the other's going down in magnitude. That in itself is not a contradiction, although it can surprise people and can throw people off, because people do tend to think of acceleration and speed as like very intertwined. But so just everybody know, like the thing is getting faster and faster, i.e. it is accelerating. Like the thing is gaining speed. This thing is gaining speed, so it is accelerating. But the rate at which it's gaining speed is going down. It's gaining, and this is, again, this does not yet address what Sam's asking, but just on the magnitude level, like this thing is gaining speed as it goes in. It's going faster and faster from 0 to 3.87. So it's adding chunks of speed as it goes. But if you think of it as gaining little chunks of speed as it goes, the chunks of speed that it's gaining are getting smaller and smaller. It's gaining less and less speed, always gaining, but gaining less and less. Again, that still does not address what Sam's asking. But just to start, but that already will confuse people. Like that already is an interesting phenomenon. Like you can be gaining speed. In other words, you could have an increasing speed, but at a decreasing rate. That is what's happening here now. But what Sam is getting at, and so I hope everybody's clear on, but what Sam is getting at is this. I think. We'll see in a second. Right, like so first the thing I just said a second ago and the thing that's on the piece of paper so far was just about magnitudes. It's just about gains or losses, right? But now Sam's bringing our attention to the direction, and I'm bringing our attention, we all have to look at the direction. Like the at any given moment, this thing's velocity, let me be very clear. Now, just for the record, so what I'm saying is, if we look at velocity, what Sam was asking, like our velocity and acceleration, both, like, because I was making a big point a second of saying, now remember the acceleration itself, those numbers are negative, but that's not what we're asking. We're just asking what's happening to the change, yada, yada, yada. But then what Sam's saying is, oh, okay, fine. Like she's saying, I get that. But if the acceleration at every point is negative, which it is, like first it's like negative 100, then it's like negative 99, then it's negative 98, negative all the way to zero. She's saying, hang on, is the velocity also negative? And because we hadn't really been making a big deal of that, but it's a legitimate question. And the answer is yes. At every single moment, at every single spot, the velocity is also negative. How do I know that? Or why do I say that? Simply because the thing is moving to the left at every spot, like it is coming in, right? Acceleration is negative because it's being pulled in, it's being forced in, its changes are negative. But independently of that, at every moment, the velocity is also negative. And that seems to be a contradiction. For what I know what she's getting at. And again, I'm like dragging this out as usual because I really want to address I think a lot of you might also have this question. You just might not be conscious at the forefront of your mind. But one of the main things that Sam's question is getting at, or what actually I'm trying to get at in the homework questions themselves, is we all want to. The acceleration and velocity are very, very related, very conceptually related, very easy to confuse in our minds, even when we think we're not confusing them. And in fact, they're mathematically related, i.e., one is a derivative of the other. But they are independent functions. Part of what we're trying to get at here is that each one is like a wheel that spins on its own, right? So in other words, knowing the number of one does not tell you the number of the other, the magnitude. And knowing the sign of one does not in and of itself tell you the sign of the other. They each could be whatever sign they want, and for independent reasons. So what Sam is saying is, okay, fine, the acceleration is negative because the thing is being forced in. But what about the velocity? Isn't that also negative since the thing is in fact moving in? And again, just because something's moving doesn't mean it's being pulled and vice versa. But she's right. Both signs are negative. The velocity sign at every moment and the acceleration sign every moment. Now you might say, so who cares? Like, why is she like, who cares? Why is that a problem? Ultimately, it's not a problem. But why it seems like a problem, I think, to Sam, and why this is worth stopping on, is because it almost seems like there's a contradiction there. Because if it's a negative acceleration, it almost feels like, shouldn't that be slowing the mass down or something? But what actually, if we're like looking at this really carefully, if you think about it, the fact that they're both pointing in the same direction is precisely why this object is speeding up. Like like negative acceleration doesn't necessarily mean slowing down. Positive acceleration doesn't necessarily mean speeding up. What means speeding up is if the acceleration agrees with the velocity and vice versa. If you back up and just think of any problem, you know, like throwing something up in a gravity field, or the big old duck problem from last semester, for those of you who are in my physics class, like if something is moving in the same way that it's being pulled, if something is moving at a given moment in the same way that it is ultimately tending to move, then it's speeding up. If the force and the motion are aligned, then it'll speed up. So in other words, in the simplest case, that is if something's moving positively and it has a positive acceleration, oh, it's speeding up. If something's moving positively and has a negative acceleration, we say it's slowing down. But if something's moving in a negative direction, something's moving the other way, and it has a positive acceleration, right? That means there's a conflict between the way it's going. And just think of acceleration as like a rope on something. If something's moving to the negative direction while it's being pulled to the positive direction, then it's going to speed up. Because what did I just say? That's not what I meant to say. If something's moving in the negative direction while it's being pulled in the positive direction, even though the acceleration will be called positive, the mere fact that it's in conflict with the velocity means the object will slow down. It will, right? And finally, then, if something is moving in a negative direction with a negative acceleration, that means it's speeding up. Much like, and the simplest example is, and the most common example is when something's falling down, right? It's moving down. If you call down negative and if you call up positive. So let's just say we call up positive, we call down negative. When you throw something up, when it's going up, it's moving positively, has positive velocity, but has negative acceleration. So it slows down. Then it gets to the top, now starts coming down. It's moving with a negative velocity and it has a negative acceleration, like it's still being pulled down. So the numbers get, so it will go like velocity like 0 to velocity -10 to velocity -20 to velocity -30. The negative velocities will get increasingly negative. Their magnitudes will get bigger and bigger. So when something is going down and accelerating down, if something's moving negatively and accelerating negatively, if those two negative signs are in agreement, then the object is speeding up. That's precisely what's happening here. Like, it's a very legitimate question because there is something that seems confusing. Well, there's a lot that seems confusing, but I think there's no error or anything. I think this object is moving negatively. It's being pulled negatively, so its speed numbers are rising from 0 to 3.87. Does that make? I'm actually really want to. Oh, yeah.
So you're saying, since acceleration's in the same direction, it's speeding up, but because acceleration's decreasing, the rate at which it's speeding up is decreasing? Like for the speed, it's not.
Exactly.
Okay.
Exactly.
I think I got it then.
That's awesome. And that was that, yes. For everybody, like what she just said, if what she just said works for you, that wasn't like just consistent with what I'm trying to say. That is what I'm trying to say. Like, yeah, that is, and it's right. So bottom line, right. So I probably can't add anything to that, but like, so it's this is why all these derivatives, like it's really hard to keep straight because there's a big difference between like a given derivative can be positive or negative, and then a given derivative can be decreasing or increasing, which is to say the sign of the next derivative. Okay, but I'm just confusing things. What she just said is exactly right. Okay, so I'm going to go on, I think. Okay, but really good. Oh, thank you. Awesome. So that's a closing the conversation. Okay, but all right. So so far we have, yeah. So velocities go speed, magnitude velocity is going up, magnitude acceleration is going down. So then the next question is kind of the hardest one. I guess that was A and B. Sorry. Did I say A? Yeah, A, B. Okay. Okay. Okay, so now we get to the hard question, and this is a hard question, and most people got it wrong. And it's asking you to think about something that you may well have never thought about before. That's where we're starting to like move on here from classical physics. This whole sheet is meant to make a long transition from in principle reviews to like new thinking, but it's also trying to show us that the new thinking is building off the old thinking. It's not. Anyway, what I'm saying is I'm not actually assuming that you've all heard the word jerk before. You may or may not have. It's a cool word. But it doesn't matter if you've ever heard the word before, or even whether you've ever seen it come up in a physics context. Frankly, there's no reason that it would have come up in a physics context before. I'm not assuming that has. I'm defining it right here and now. I'm saying, and it is a real word. I didn't make it up. Jerk is the derivative of acceleration with respect to time. That is to say, it is the third derivative of position with respect to time. Now, there's many reasons why it's never come up in physics before. Well, the chief reason why it doesn't come up in physics is because F net equals ma. Because what really Newton's second law is saying is that all the basic, most recognizable activity that happens in space and time among objects all has to do with the second derivative level. Like most of our focus in classical physics is on the second derivative level, not because it's mathematically special, like we could be looking at derivative number one, we could be looking at derivative number two, we could be looking at, like, once we learn about derivatives, we hopefully understand from math that you can take derivatives forever, that any function, that a derivative is a function. So if you take the derivative of a function, you can then do the same thing to that. You can go on forever. We tend to stop our focus and our concentration on derivative number two, specifically because F net equals ma. In fact, arguably, that's like the real meaning of F net equals ma. It's saying when it, like, we have all this cool abstract, infinitely universal math, but if you actually want to apply it to the physical world of mass in space and time, it turns out derivative number two is where the action is a lot of the time. Okay, so it's not a surprise that we've never thought about derivative number three before, but derivative number three is to derivative number two as derivative number two is to derivative number one, if you know what I mean. Like, that's the concept of math. It's just once you get the relation, you have a relation that you can do. So I'm asking us for the first time, can we say anything? Can we think about, can we conjecture, just based on the information we have, anything about this next derivative? Now, a lot of you put constant. And to be honest, most of you didn't show any work or any reasoning for that. Most of you also didn't show much reasoning for the other two answers, but I'm willing to believe that you did something simple in your mind, like what we just did on paper. But now when we get to something hard, you might want, like what, I don't know if it was a guess or what, but how can we go about thinking about this third derivative? And by the way, the answer constant is not right. Which I'm not chastising anybody before, but like, okay, this requires some thought. How can we think about this? Well, here's, before I go any further, I just want to establish what I just said. In English, I'm just like writing this down like as though it's like a Miller's analogy or an analogy from the SATs or something. I'm just saying, like, the third derivative is to the second derivative as the second derivative is to the first derivative, right? Derivative is a process or it's an operation that we perform on a function, and it's the same operation, whatever function we perform it on. So maybe if we want to see what's happening to the third derivative, can we see if we see any patterns or any relations thus far building among the first couple, which is in effect what Sam was doing. She was trying to get straight in her mind, like, hold on, when the second derivative has this sign compared to the first derivative, what does that say about which one is like increasing or decreasing? So if I want to look at for patterns and see what the third derivatives do, you know what I might do? I mean, the more easily you want to see a pattern, or the more likely you want to believe a pattern, the more data you might want to base your pattern on. So why don't I back up a step and add one data point to this body of information that I'm building up here? Like, so I'm just saying, we looked at what the velocity is doing. Velocity is first derivative of position with respect to time. We looked at what the acceleration is doing. It's the derivative of that. It's second derivative of position with respect to time. We've never actually just stopped and asserted to ourselves what the position was doing. And it's probably the easiest question of all to answer, which is why we might not have, which is maybe why I didn't ask it in the sheet, or why we might not even think that it's useful. But it totally is. Like, in other words, let's look at the zeroth derivative. Let's look at the function itself. Actually, I'm going to stop and ask all. I'm going to ask you guys. Like, just to make sure we're not totally confused by any of this, or the same thing, or whatever. Like the positions. Okay, the positions now. The positions, unlike the velocity and acceleration, the positions are all positive. Right. We start off at position positive 0.15, and we're moving through positions to position 0. So I'm not trying to confuse anybody. This is not meant to be a trick question, but just to get this straight, to make sure we're not crazy. Could someone, and maybe just like not Sam, because I mean, I know she's paying attention. Can anybody just tell me, just straight up, the magnitude of positions is the magnitude of positions decreasing, increasing, or staying the same as we go toward the equilibrium position? Can anybody? And I'm happy to repeat. Oh, okay. Awesome. Thank you, Camilla. Awesome. Before I say right or wrong, does anybody? So first of all, Camilla, let's get this straight. First of all, thank you, Camilla. She's totally paying attention. Totally gutsy. Totally went out on a limb on her own there. Before I even say right or wrong, let's just establish that Camilla totally gets points for, because I think I explained this Thursday, right? Remember, and I'm not trying to be weird, but since I am starting to like force you guys into like actually like, starting to get into physics here, let's get it straight. Camilla obviously gets 5 points tonight for just turning in her game turn like I participated in class, like because I said the thing about position. Then remember, she can also submit that no matter what I say now about her answer. she could submit that same entry into four. I think I explained this. Tell me if I, and I think I put this portal out. Please tell me if I didn't. I think I did. She could submit that into the portal. It says for right or for wrong, because she just said something that is specific enough and gutsy enough. Like she answered a question where now I'm either going to say she's right or I'm going to say she's wrong. Like as opposed to just saying what a nice feeling you have. Everybody has the right to their opinion. Right. So she's definitely going to put that in the portal that says for right or for wrong. If she's right, she gets the satisfaction knowing she's right. If she's wrong, she gets to also put it in the 11-point portal for being wrong, right? Just to say, and I'm saying all that to remind you, and this applies to everybody. It doesn't matter who goes first. So since I'm not saying whether it's right or wrong yet, anybody can still put in anything they want here for, I mean, whether it's for points or just to show me you're paying attention. But and also I appreciate it because she's showing she knows what the question is. The question again is the position, is the magnitude of position increasing, decreasing, or remaining constant? So I'm looking at chat. I see there's things happening in chat. That's awesome. So Camilla totally is part of this. That's great. Ashley is totally same deal. Okay, so Ashley gets points for participating, points for going right or wrong, no matter whether she's right or wrong. And then either she's totally right, which is awesome, or she's going to get 11 points for being wrong, right? And presumably between Camilla and Ashley, they both are not saying the same thing. So one, I mean, they're not both right. So that, and then we got Stephanie also. W in the second. W. Yeah. Yes. It's awesome. You all have different answers. That's a great observation on Ashley's part, and that's cool. And actually, no, what's clear about all your answers is it's showing you definitely hear the question. Thank you. So that's 3 people, and I'm assuming Sam does too. That's awesome. And the fact that you all have different answers means at least we're going to get our tuition money's worth when I do give the answer. I mean, in other words, I'm not wasting your time. One thing I want, and anybody else, this is not a race and it's not a competition. Anybody else can still put, and it doesn't matter if you're even influenced by one of them. That's okay. But anybody else can still put something in the chat. But one thing I'm interested in what Stephanie said, though, I think it decreases because if W in the second derivative magnitude should, I don't know what the W. Oh, and some of you are going in the direct chat, which is cool too. Okay, so I'm not going to say anybody's name if you're in the direct chat, but I got at least one person in the direct chat. I am going to say at least, well, I'm actually not. Okay, I got one concrete answer. I might say the answer. Well, I'm not going to. Okay, I see the direct chat. That's awesome. I'm not going to say if it's right or wrong yet. But I don't want to put Stephanie on the spot, but I wonder if she might explain the W in.
That was a mistake, sorry.
Oh, okay. Oh, is this fair? Can I just ask this, Stephanie? So if I forget the W thing, you're talking about a pattern then? You're saying your guess is because of.
Yeah, like for example, how you said that in the second derivative, it decreased because, so I'm assuming that if we do the third, then it'll be the same.
Oh.
Like a pattern, like you said.
Right. Okay. So this is really good. And we are trying to look for a pattern here to just to be clear to everybody. And right, we are trying to see if there's a pattern. Now, to be clear, like the question we're trying to figure out here, the ultimate question that's on the homework sheet is what's happening to the third derivative. So what I'm saying here is in order, and I'm thinking there might be a pattern. So in order to figure out the pattern, I'm trying to go back and ask what's happening to the position. So I guess I just want to say to everybody, I'm kind of thinking that we could answer the position question with our own information, just like we did the velocity and acceleration. And then whatever answer we get, we can put in and see if we see a pattern. Like, I'm not sure, we might not be able to use a pattern, or we might not have to use the pattern to get the position. I think it's more like we're going to get the position in order to see the pattern. But that doesn't mean Stephanie's wrong. It totally does not mean Stephanie's wrong. Let me just say to everybody, though, I'm not trying to trick anybody. I mean, it always seems tricky in physics, but let me just remind you what the question is. I'm literally asking, like, if everybody understood the speed went from 0 to 3.87. So we said it increased, right? We're just looking at magnitudes. Like this, the numbers of the speed went from 0 to 3.87. So we said it increased. The numbers of the acceleration, the magnitude of acceleration went from 100 to 0. Like technically it went from negative 100 to 0, but I don't care about negative signs. So it went from 100 to 0. So we said that decreased. Now the positions are going from positive 1.5, like positive 0.15, 15 centimeters to 0, right? The position, I'm just literally saying where the mass is going from 0.15 to 0. So, and I can go to slides. Yeah, sorry. So if that's the question, and some of you might have lost me in the whole larger context, or you might be getting lost in where this is all going or why. But if you just zoom in and just focus on this question, I think I'm interested in getting a little bit more input, and then I'm going to go on to make sure I'm literally asking just what is happening to the values of position, the magnitudes. If they're going from 0.15 to 0, are they going up, down, or remaining the same? Like, that's my question. So I think I'm going to move on when maybe 2 more people respond, whether it's private, it could be private, or public. But I kind of want to make, or if anybody wants to just privately respond, like, I hear the question, but I don't have an answer, or I still don't understand the question, or something. But I do want to make sure, but I think this is a question that everybody can visualize, even if they've lost everything else. So I'm going to wait for 2 more responses of any kind, either private or public, and then I'll move on. But the question is, and then I'll say whether, like, but clearly Stephanie and Ashley and Dorina have already done their job, whether they're right or wrong, and Sam. So the question is the position increasing, decreasing, or staying the same as we go from the initial position to the equilibrium position, as we go from 0.15 meters to 0? And I guess I want to say, I think some people might be overthinking, or I think somehow I'm boring or intimidating people into fuzzing out, because the question is not a trick. It is as simple as it might sound. If you're just hearing for the first time, like, tune everything else. Okay, I just got one more answer in the direct chat. That's good. So, and in a minute, I'll read out the answers that are on the direct chat. I won't read the names, but I'll read out the answers just so people know. But I'm going to wait for one more. And remember, you get 11 points if you're wrong. So, I mean, seriously. But I feel, because the other thing is, this is like a multiple choice question. I mean, you don't have to make anything up. I'm giving you the options. The options are, is it getting bigger? Is it getting smaller? Or is it remaining the same? And by it, I mean the value of position. Okay, cool. I just got one more in the private chat. Thank you. Okay. Now I'm going to read out the answers. I'm not going to read the names from the direct chat, but again, it doesn't matter if you're private or public. You still, all the points things still apply to you. Okay, in the private chat, I got 2 votes for decreasing, 1 vote for constant. That's in the private chat. In the public chat, we got 3 different answers: increasing, constant, and decreasing. Now, right, is everybody still with me? And please get with me here, because I know this might be getting boring, but the next question is when we're really going to get into math. It's going to get heavy in the next question, which is really the point of the whole thing. But if we can't, but this is like a lot simpler than the next question. So we kind of want to get our minds around this. I'm going to say I've got like 6 votes here, 3 public, 3 private. And I appreciate those votes very much. And I know that I asked Sam not to vote, so I'll count her as 7, so it's not on her. But, and actually, how big is the class? Okay, that's a lot of the class. But I've gotten very different answers, right? As someone pointed out, which again means we're going to get our money's worth here. But I got like 1 answer for increasing, 2 answers for constant, I think, and 3 for decreasing, right? I'm actually just slightly concerned. I'm going to change the view for a second and see. Can I just ask, actually, to make absolutely sure, if you haven't said anything, if you haven't given an answer, can you just in the private chat just put the word yes if you're following this and following the question? You don't have to give me the answer. Just put the word yes if you're following me, if you hear me, if you're following the question. But if you're not, if you've lost me in any way, just put no in the private chat. You don't. Okay, that's a yes. That's cool. Yeah. Okay. Cool. Okay. Thank you. All right. That's good. Okay. Because here's the deal, to cut to the chase. I think the answer is decreasing, which I like 3 people voted for, and that's awesome. I do think the answer is decreasing. Again, I think anybody who put any answer at all is getting a lot of points. If you care about points, like, they're getting to submit to the right or wrong portal no matter what. And if anybody got wrong, there's no shame. They get to put it in the wrong portal for 11 points, which again might strike some of you as weird, like that they're getting. But the people who put decreasing are right. Okay, and I do want to just make this clear. All I'm at, like, I think the other stuff is very hard to follow if you can't follow this one. I'm literally just asking, and what I'm saying is, and I think the people that put decreasing do follow this. I'm just saying if the position is 0.15, and then it's lower and lower and lower, and then eventually it's zero. If the position went from positive 0.15 to zero, then the position decreased. Like the numbers went from 0.15 to zero. Even if the numbers had gone from negative 0.15 to zero, frankly, I would still say they decreased because all we're looking at is magnitudes here, but it's not actually even that complicated. Literally all the positions are positive. The thing is always in the right-hand side. It's going from somewhere, 0.15, moving in towards zero. The positions are decreasing. It's not any more, I mean, I'm not trying to chastise anybody, but does everybody follow that? If you put something out, like they're not constant, the thing is moving. The positions would only be constant if it was sitting still. It's moving, so the positions are changing. Are they getting bigger or smaller? Well, they're getting smaller because it's moving toward a place that we call zero. Is that? So I think. So I don't. So is it like? And then the speed. So I'm saying this. I know this is one of these things that is simpler than it seems, maybe, and it's really easy to overthink, or you might feel like it's a trick or whatever. But so please stop me if you're not following now. And again, if you did follow before, but you follow now, cool. But I'm saying what it looks like we have here is a situation where the position is going down, the position values are decreasing. It's moving from 0.15 to zero. The speed values are increasing. The speed values are going from 0 to 3.87. The acceleration magnitude values are decreasing. They're going from, and granted they're negative, but they're going from 100 to zero, right? So it looks like position's going down, speed is going up, acceleration's going down, right? And, right, so far is that right? And remember, well, actually, forget that. Forget that. It's okay. Well, what I'm trying to urge is that the question I just answered about position, I didn't get. I think it's great that I think it was Darina or someone. No, it wasn't. It was Stephanie was bringing up the whole pattern thing, which is great. We're totally all about the pattern thing. But I kind of want to go in the reverse direction from the way Stephanie went. I'm saying, I feel like position, speed, and acceleration, we could answer each one by itself without looking at a pattern. The truth of the matter is, I think that if we could answer speed and acceleration, which most of you did on your own, I think the truth is position's even easier to answer if you don't overthink it, or if you don't think there's a trick in the question. Like, you just look at it, the values are just literally, they're given in the problem. They're going from 0.15 to 0. So if we answered each one of these independent of a pattern, we didn't like reference a pattern, we just found that they were true. But now we look, it does sort of look like they're falling into a pattern, doesn't it? I mean, or I think it looks like they're falling into a pattern. I'll go back to that page in 1 second. Let's write this. I'll go back to this page. All right, I'm just going to read this out. What I'm saying is now, I think we have a pattern here. I think the arrows are going right. The arrows are going down, up, down. Now, if the pattern continues, I think the answer is straightforward. I think the jerk, if the pattern's continuing, I think the jerk should, stop teaching. No, I think the jerk should go up because the acceleration went down and the velocity went up and the position went down. If the pattern's increasing, I think the answer is jerk goes up. Now, you might say, well, why would the pattern continue? But I would put it the other way around. I mean, since a derivative is a operation that you perform on a function, when you perform a derivative on the second derivative, you get the third derivative. When you want to get the fourth derivative, you do the same thing to the third derivative that you just did to the second. Since it is one operation that we're just recursively doing over and over again, I would say if you think the pattern breaks down at a particular derivative, I would want to know what the reason for that is. Like if the pattern breaks down, that's because one particular derivative is somehow special compared to the others. And I would want to, I'm not saying that can never happen, but I would want to know what the reason is for that. Put more, so I don't know if I'm on the wrong page here, but put more specifically, tell me if you wanted me to turn back the pages. Okay, here's what I'm ultimately saying. What time is it? Not to, what I ultimately think the answer. I think the answer to the jerk is. I think the jerk is increasing. That's the answer. I mean, that is the answer. I think a good reason to see that it's doing that is if you look at the pattern. I think as long as you believe that this pattern just continues, then that's the answer. Now you might argue, and it's not crazy, or you might say, hang on, like how do we know? Why do we believe that the pattern continues? Now I'm saying, and sometimes patterns don't continue, but I'm saying, think of it this way. If you don't think the pattern continues, what you're really saying is you think it stops at a particular place, this pattern of derivatives. If you don't think that, if we don't think the pattern perpetuates, then we think that that we can take derivatives to a certain point, and then all of a sudden the derivatives become zero. There's no more. And I'm not saying that never happens in nature. In fact, that does happen with like free fall and constant acceleration. I'm saying in a lot of what we did in classical mechanics, and a lot of what we did last year, whatever, okay, we did a lot of constant acceleration examples. We had, in fact, a whole set of what we called constant acceleration equations. And one very big example of that is free fall, right? Where in free fall, something moves from here to there, so its positions change continuously, like it falls from a height to the ground, so the positions are ever changing. It's moving, it has velocity, but as it moves from a height to a ground, the magnitudes of the velocities are changing, i.e. the thing is pulled. When something free falls, it accelerates, right? So you have changes in position, you have changes in velocities, so you have accelerations, so you have a function, you have a derivative, you have a second derivative. But then we say when something's in free fall, the second derivative acceleration, it turns out we say is approximately a constant. It's like G, it's like 9.8, or whatever you want to call it. And if you were to take the derivative of that, you would get zero, right? Like in many, many examples from classical mechanics, specifically free fall, you have a function, you have a derivative number one, you have a derivative number two, but the derivatives bottom out after that, like the jerk, the width, the yav, the whatever, derivative number three, derivative number four, they're all zeros because derivative number two is a constant. So I'm not saying that this never happens. In fact, we're very used to it happening. We're used to the pattern stopping at number two. But why? Because F net equals ma, because all accelerations are associated with net forces. And in a case like free fall, or in a lot of the cases we were looking at in classical mechanics, the force, the net force is constant. Therefore, the second derivative is constant. F net equals ma. So we direct all of our attention to the second derivative. And if that force is constant, then the second derivative is constant, and the pattern ends. Here, we have a force that's changing continuously. And not only is it changing, but it's changing as a function of position, not of time. It's changing as a function of position, not of time. So there's no immediate obvious reason to see, and there's no immediate motivation to assume that the accelerations stop, or that the derivatives stop at the acceleration level, right? This is a fundamentally different case now, where the force is not constant, the force is changing. So it's at least plausible that the pattern goes on forever, or put another way, if the pattern doesn't go on forever, I need something to tell me why I would pick one derivative over another, and assume that derivative, like why would one derivative be special? Why would the pattern stop at a particular derivative? When it comes to F net equals ma, the answer is it would stop at the number two level because of forces, and when the force is constant. That's not what we have here. Okay, I'm going on and on. So I'm saying here, there's good reason to believe that this pattern goes on forever. I think it does. If the pattern goes on forever, that means the jerk goes up, and then the next one goes down, and then the next one goes up. That's what I'm conjecturing for the moment, and it's going to turn out to be right. But let's look at this really specifically now. Let's take this really seriously, this idea that we no longer have constant acceleration. We have higher derivatives running here, and producing motions that are more complicated than free fall or something. So I'm saying the answer, okay, the answer is that the jerk goes up. You could put an asterisk on that and say, like, this is a conjecture that needs to be verified further, but I think it's going to be verified now if we go to the very last question, question 9, which I know we only have 9 minutes, but that's okay. going to go to the next page. I'm just saying here, our question number 9, of course, we're not going to finish it today. I apologize. Question number 9 is at t equals 1, what's x, right? Very straightforward seeming question. It is, it couldn't seem like a more simple question. I mean, it couldn't seem like a more standard physics question. You name the time, I need to name the position. Like, where is something when? Like, that's what physics always is. And there's nothing special about this 1 second that we picked. It's just an arbitrary example of some moment in time. So really what I'm asking in general here then, so what we're looking for here, like what people might think for question 9, they need an equation to plug in or something. And sure, if we had an equation like x equals 1 f at squared plus b naught t, I mean, if we had that equation, we believed it was true here, you would plug in t, in this case 1, and it would spit out x, and we'd be done. But we don't have that equation. Like, right? That certainly looks like something that would be nice. I mean, we certainly want some kind of equation that expresses x as a function of t, but our good old favorite or classic from the beginning of physics 1 example that totally does not work here. It looks like the kind of thing that would work, but it doesn't work here precisely for the reason that we don't have an a. A is not constant, right? So we're not looking to plug into some equation we already have. What we're really looking to do here is derive or come up with an equation that actually adequately describes this scenario of a mass on a spring, right? So we're not trying to plug into an equation. We're actually looking to develop the appropriate equation. What kind of equation? X as a function of t. Okay, all we know is what we know. I know we have 4 minutes. So we're just going to set this up and we're going to continue next time. What do we know? So tell me if we should go back to that page, but so I can only use what I know. What do I know? I know, I know that I know F always equals MA, right? F net always equals MA. And we know that in this case, mass on a spring, the spring force, right? right? This is what we have. We have the spring force is the only force acting, negative kx equals ma. Notice even just when I write that, that is the issue. That's very simple and straightforward. That's what we know so far, but that's why we have all this funny business going on with derivatives and all this new, even though this is very simple, it's just a mass on a spring. It's suddenly it's like all this kind of new math thinking and new physics thinking for precisely the reason that acceleration now, if you just look at the way that's written, and I know we have 2 minutes, so we're going to stop, but just look at the way that's written. Acceleration depends on position, right? That's the catch here. Like usually in physics, if someone says, hey, what's the position? Like if you tell me the time, if I tell you the time, can you tell me the position? Normally what we say is, oh yeah, we can figure out the position. Just let me know the acceleration. Like I can figure out the position. I can predict where something's going to be. Just give me the rule, the pattern of its motion. Give me the acceleration and I'll use the acceleration to predict its position. Like that's what we used to do with free fall and stuff. So someone says to me, what's the position? I say, oh, no problem. Just tell me the acceleration. And in this case, they're saying, oh, yeah, I can tell you the acceleration, but it depends on position, right? That's what's happening here. That's what's weird. Position always depends on acceleration, but here acceleration depends on position. So it's some sort of a circle or a Gordian knot or something like that. Let me be more specific, and then we're going to stop right here with one more line. Acceleration is by definition what we've been saying, the second derivative of position with respect to time, right? So what we have, so substitute in what we have here, literally. This is what we have. Oh, actually, oh, that's, I'm going to stop right there. I'm just going to stop right there. Just keep going with the homework, whatever. I will unpack that on Tuesday. I'm just going to stop. But notice that that is an equation with a bunch of letters. It's complicated, but the only variables in that equation are x and t. X is the dependent variable, t is the independent variable. So that should be all the information we need to get what we're looking for, which is x as a function of t. But we need to unpack that and rearrange it in a proper way in order to do that. I'm just going to stop there. Sorry, the class was like a little weird today. Well, I guess it's always weird, but I apologize. But we're just going to stop there. I'm not going to stop the recording. I'm going to hang out if there's any questions or anything. Oh, yes, absolutely. Let me just stop the recording. Yes, thank you, guys. You can all go. I'm just going to hang out for any questions. Hang on a second. Let me turn off the. Bye. Thank you, guys. Bye.